Hey everyone, today we are going to be talking about vapor pressure and specifically how that relates to temperature and boiling points. So temperature is a measure of average kinetic energy. And we think about an average, we think about maybe a few numbers being added up together and then you divide by the total number of numbers that you have, and that gives us an average. And so that's what temperature is. So each individual molecule has a single temperature, and when we add up those single temperatures of each molecule, then we get an average. And so we can see that here in this energy diagram below. And this states that we have a number of molecules and kinetic energy. And we can say that kinetic energy is just average temperature, or average kinetic energy relates to temperature. So your x-axis is related to temperature and your y-axis is related to the number of molecules. So at some point, we are going to build up enough kinetic energy past our average, and that's going to allow those molecules to escape. And so because those molecules escape, that lowers our kinetic energy or our temperature. And so this is why dogs pant, pigs roll in mud, and humans sweat. So the evaporation of moisture allows particles with the highest kinetic energy to escape, leaving a lower average for those molecules to be left behind. And as long as the moisture can evaporate, the process makes you feel cooler. However, if it gets too humid, the air can't hold any more moisture, and you just end up being hot and sweaty or wet. So how does that relate to vapor pressure? So we have on the left here, we have an open container, and eventually all of these molecules that are on the surface are going to evaporate off, and eventually that would leave our flask here to be dry. However, what happens if we cap it off? Well, we have molecules at the surface that are still evaporating off. However, they don't have anywhere to go. So then those gas molecules will condense, meaning that they turn back into a liquid, and that's going to cause them to build up this pressure in the flask, and that is what is called vapor pressure. So, and so the balance between the gas evaporating and condensing, again, it causes that pressure, and that is vapor pressure. So what does temperature have to do with vapor pressure? Well, as temperature increases, the average kinetic energy of the particles will also increase. And this will change the shape of our energy distribution, and that will eventually speed up vaporization, which leads to a higher vapor pressure. So here, this graph here, which I will draw out. Okay, so we've got this graph here, and then as we increase temperature, we get something more like this. And so this graph here is actually colder. And that's just because it doesn't go as far across that x-axis, whereas the one lower is going to be hotter. So anytime your diagram goes further across the kinetic energy, which we said relates to temperature, means it's going to have a temperature increase or a higher temperature. So even though it looks shorter, it's still a hotter diagram. And at higher temperatures, if you notice here, the shaded area increased from before, so that means we have more molecules that are able to evaporate or leave our system. Lastly, how does that affect boiling points? So when vapor pressure gets high enough to equal atmospheric pressure, then we get vapor bubbles that start to come off, and that doesn't just start at the surface, it'll also go towards the bottom as well. So if we look here, let's clear this out. We have a cup of water here. So we have a cup of water. It's got H2O molecules inside of there. When we are evaporating, then we are just dealing with the molecules at the surface, right? So that is evaporation. However, as we start to increase our temperature of our water, so we add like a flame underneath it, then our water molecules not only will leave at the surface, but they'll also leave down here at the bottom as well. And that is what boiling is. So when we get enough pressure, vapor pressure here, that equals the outside or the atmospheric pressure, that is boiling point. So atmospheric pressure equals vapor pressure. And this leads to boiling. So when we think about our discussion post today, we said that when we try to go cook in higher altitudes, or say the mountains, for example, then our water is actually going to boil cooler. So when you are up in the mountains, the atmospheric pressure, or the vapor pressure, gets to the atmospheric pressure quicker, meaning that your boiling point is lower. And we can see that, for instance, if we went to Denver and we tried to boil a pot of water, our boiling temperature, or boiling point, is actually 69 degrees Celsius, whereas if we are here in Missouri, closer to sea level, our boiling point is going to be 100 degrees Celsius. So the lower the atmospheric pressure, or the higher up in altitude we are, the easier or the quicker it takes for our vapor pressure to equal atmospheric pressure, which is going to cause for a quicker or cooler boiling point. And we can see that for the opposite, if we went somewhere that had a low altitude, so say we went to somewhere such as the Dead Sea and we wanted to boil a pot of water there, would actually take longer because we are lower in altitude, so it takes longer for our vapor pressure to build up to equal that atmospheric pressure. And if you go somewhere like that, I believe the boiling point there is like 142 degrees Celsius, or somewhere around that range, in the 140 degrees Celsius. So when we think about a pressure cooker, for example, so a pressure cooker will actually build up pressure, which would be that vapor pressure, which means that the liquids inside are able to get hot enough, and they're not going to boil away because they are covered. And the normal boiling point is the temperature at which the vapor pressure equals standard pressure, or 1 atmosphere. So that is today's notes, just going over exactly what vapor pressure is and how that affects our boiling points, and the impact that temperature can have on the vapor pressure and those boiling points.